spectroscopy today. Usually when we do infrared spectroscopy, we're attempting to determine an unknown compound based on bond stretches, but for the sake of explanation today, we're just going to use a known compound, benzoic acid. So the first thing we're going to do is just get some material using a spatula. Okay, so we grabbed our benzoic acid. We've come over to the station now where we're going to run the infrared spectroscopy. What we need is a microspatula in order to get the compound onto the surface. The first thing we're going to do, or the first thing you should do before you run the infrared spectroscopy, is to always wipe the surface with a wipe. This is just going to ensure that you get the compound that was used by someone else off of the surface and to make sure that your results aren't skewed at all. So now that we've cleaned the surface, we can open our program. We use Opus. So I'm just going to open that up. You should be able to log in pretty easily. Now the next thing we're going to do is we're going to run a diagnostic scan, and we're just going to click measure sample right here. And this is just the first step. You can put in a sample name right now so it's easier to differentiate later. We're doing benzoic acid. So I'll just label that like that. And now it's running the background scan. This is the first step in being able to run the infrared spectroscopy for the benzoic acid itself. Okay, and then we get to this stage right here. So now what the program is going to ask you to do is to put a sample on the stage. And there are two different types of samples that you can put on the field right here. You could either put liquid in oil or a solid. The difference with what you're going to do is if it's a liquid in oil, you're going to keep the clamp up like this. But if it's a solid, you're actually going to engage the clamp down onto the compound so it can just push down on the field and it can read it more efficiently. So the way I'm going to do this is I'm going to add the benzoic acid carefully. We're not going to add a lot. We're going to get it right in the center right here so it can read it well. Just going to make sure it gets there. And now that I've got it on the center, or approximately on the center, I can just engage the clamp. And you want to make sure you don't put too much benzoic acid on there. There's no need for it. That's what the clamp's for. It's going to make sure enough gets on there, or gets onto the surface. So now that I've done that, you can just press OK. And then it'll run it for you. Again, it takes a couple of seconds. So this is the completed infrared spectroscopy. You have your fingerprint region and you have your functional group region here. The computer doesn't automatically show you the peaks, so you can opt to peak pick, which will help you in your analysis later, and that'll automatically do that for you. And you can print it out, and then after that you can do an analysis on your own using your knowledge of the bonding stretch vibrations.
Now, normally when we're looking at IR, we only look at the region of 4,000 to 1,500 wave numbers. Everything else, i.e. 1,500 to 400 wave numbers, measures bond bending vibrations and can normally be disregarded. 4,000 to 1,500 measures the stretching vibrations of each bond. IR works because the stretches between atoms and functional groups vibrate at certain frequencies. Depending on the group, when those frequencies are present, that fraction of the IR spectrum will be absorbed. This creates the shown peaks. Consult a table to show the typical wave numbers for functional group stretches. Impurities can also mess with IR data. This is why we recrystallize. By doing this, we can remove soluble and insoluble impurities. Also, bear in mind that IR will only give you a general structural picture of the molecule. It can't give you an extremely precise diagram. It's hard to know. For that, you need NMR.
This isn't the best IR for benzoic acid, but lots of conclusions can still be drawn. There is a strong broad peak at 2825 wave number, which is indicative of an OH stretch of a carboxylic acid. The peak has a width of about 500 wave number, largely because there are further stretches caused by the carbon and hydrogen atoms bonded in aromatic rings. Lastly, at 1680 wave number, there is an intense peak, indicative of a carbon double bonded to an oxygen of a carboxylic acid. Everything else lies in the fingerprint region and needs little consideration for our purposes.